Well, hello everyone. In this video, I'm going to give a very brief introduction to what are called Lagrange polynomials. The idea of Lagrange polynomials is you might have some collection of data points in the plane, and you'd like to find a polynomial that goes through all of those data points. Now, the more data points you have, the more difficult it is. So, for example, if I have 3 data points lying in the plane, it's going to be very difficult to draw a single line that goes through all 3 points. However, there is going to be a parabola that goes through all 3 points. But as soon as I add in maybe say a 4th point, so if I add a 4th point over here, well, now this parabola certainly isn't going to go through that purple dot, and in fact, it may not be possible at all to find a parabola that goes through all 4 of those points. However, there will be a cubic that goes through all of those points. So it may be possible for me to find some, say, cubic polynomial. So it's going to go down, and then it can go up, and then maybe it turns around and comes back down again, right? That would be allowed for a cubic. So it's not that outrageous to figure out how to draw quadratics or cubics or quartics or higher degree polynomials through given data sets by hand, right? But if you actually want a formula for that polynomial, that seems like a much trickier process. But the idea of Lagrange polynomials actually makes it very straightforward and procedural. So let's start in a very simple situation. Okay, let's say I just have 2 points. I have 2 points. We know that 2 points determine a line, and probably in your maybe high school algebra or even pre-algebra class, you learn how to write down the equation of a line that goes between 2 points. But we're going to do it in a slightly different way here, one that at least when I was in school, they didn't show us this way. I'm going to do it here with just an actual example, but you'll see it has nothing to do with the actual numbers we choose. So let's say that this point over here is, I don't know, say 2 comma 5, and then this point over here, maybe we're over at 4 comma 7. So I would like to know the equation of the unique line that goes through, and well, it looks like I missed that point there, doesn't it? Let's see. Let's try to go through again. The unique line that goes through those 2 points. All right, well, here's what I know. If I have some function, right, so say this was going to be given by f, I know that f of 2 is equal to 5. I know that f of 4 is equal to 7. Okay, fine. Here's what I'm going to do. I'm going to take those 2 outputs, right, that I know, and I'm just going to write them down with a little space in between. So I'm going to write down a 5, and I'm going to write down a 7. Now, I know whatever my function looks like, when I put in the number 2 into the function, the output should be 5, which is this 5 over here. I don't want this 7 to play into it at all, right, when x is equal to 2. So here's what I'm going to do. I'm going to multiply, and there's going to be a fraction, but on the numerator of this fraction, I'm going to put x minus 2. And the reason I do that is because when I evaluate this at x equals 2, the numerator becomes 0, I multiply by the 7, so this whole factor, or actually summand, right, there's going to be a plus sign before we get here, this whole summand is going to become 0, so I don't have to worry about it. Okay, but I also know that when x is equal to 4, I want to get 7, so I'm going to play the same game over here. I'm going to include a little fraction, and in the numerator, I'll write x minus 4. That way, when x is equal to 4, this numerator is 0, and so this whole summand is going to be 0. Okay, does this work? Well, let's see. What happens when x is equal to 2? When x is equal to 2, this becomes 0, this summand dies, and I get 5 times, it's 2 minus 4. 2 minus 4 is negative 2. I don't want to multiply 5 by negative 2. I want to multiply 5 by 1. Well, here's how I can make that happen. I'm going to divide by 2 minus 4. Right? The 2 came from exactly here. I just divide by 2 minus 4. And now when x is equal to 2, I get 2 minus 4 over 2 minus 4. Hey, 2 minus 4 over 2 minus 4 is 1. Multiply it by 5, and I get 5. And I play the same game over here. If I want to get 7 out, I need to put the 4 in. Okay, over here when I put x equal to 4, I get 0, so this summand goes away. And over here I'll get 7 times, well, 4 minus 2. I don't want 4 minus 2, I want to multiply by 1. So I'm also going to divide by 4 minus 2. And so in total, I now have a function, f of x, that when I evaluate it at x equals 2, this summand dies, and I end up with 5 times 1, which is 5. And when x is equal to 4, this summand dies, and I get 7 times, well, again, 1, which is 7. And you can see here the 5 and the 2 minus 4, those are just constants. Over here, 7 and 4 minus 2, these are just constants. And what are we multiplying that constant by? A linear function, x minus 4. And over here, a linear function, x minus 2. So if I wanted to, I could expand this out, right? In fact, let's do that. So 2 minus 4 is negative 2. So I get negative 5 halves times x minus 4 plus, okay, 4 minus 2 is 2. So 7 halves times x minus 2. Okay, well, let's just distribute. How many x's do I have? Well, I have negative 5 halves x, and I have 7 halves x. In total, that's, let's see, 7 halves minus 5 halves is 2 halves, which is 1x. Okay, cool. I just get an x. And then what comes next? I have negative 5 halves times negative 4. So let's see, that's going to be 20 over 2, which is 10. And then 7 halves times negative 2, which is negative 7. So what did I say I had? I had 10, and then minus 7 is 3. So in fact, this function just ends up being x plus 3. Okay, does this make sense? Well, let's see. If we'd gone back and done this the old way, we would have said the rise is 2, the run is 2, so the slope, rise over run, is 2 over 2, which is 1. Hey, that's my slope right there, 1. And where would the y-intercept be? Well, if I know the slope is 1, if I go back 2 to 0, I'm going to go down 2 to 3. Hey, there's my y-intercept. So this method actually works. How crazy. Okay. Now, I'm not at all recommending that if you're trying to find the equation of a line between 2 points, that you should necessarily jump into this Lagrange polynomial method, but it's good to know that there's another method out there and that it works. The advantage of this method is that if we go to more dots, like say this 3 green dot situation, this way of thinking still works. So let's try it. Let's say I have now, I'll go back to green, I'm going to have 3 dots. And I want to find a parabola, a quadratic that's going to go through these 3 points. So maybe this over here is going to be 1, 2, and this can be 2, 0, and this one over here can be 4, 3. Okay. So whatever this function is that goes through these 3 points, I know that f of 1 is equal to 2, f of 2 is equal to 0, and f of 4 is equal to 3. I'm going to take these outputs, and just like I did up above, I'm going to write them out. So I have a 2, I have a 0, and I have a 3. Okay. Now, I know that when x is equal to 1, I want my output to be 2, which is given right here. So what I'm going to do is multiply. Again, I introduce a fraction, and I'm going to multiply here by x minus 2, so that when, or x minus 1 rather, so that when x is equal to 1, this factor is going to be, or this numerator is going to be 0, and so this whole sum end is going to go away. I'm going to do the same thing next to the 3, because I don't want that 3 around either, right? I want the 2. So I multiply here by x minus 1. Okay, but I also know that when my input is 2, I want the output to be 0, right? Which is given in this middle sum end. So I'm going to multiply here by x minus 2, so that when x is equal to 2, this numerator will be 0. And I'm going to do the same thing in this sum end. I'm going to also multiply x minus 1 by x minus 2. So now when x is equal to 2, again, this sum end is going to go away. Okay, and then finally, I also know when x is equal to 4, I only want this 3 term to appear. So I multiply here in the numerator by x minus 4, so that when x is equal to 4, this summand goes away. And the same thing in this middle one. And you might say, well, it was already going to go away because there's a 0 here. Yeah, that's true, but this didn't have to be a 0. This could have been a negative 1. Okay, this method is going to work no matter what. Okay, now what goes in the denominator? Well, let's see. When I make x equal to 1, I know that these two summands are going to go away. But what's going to happen here? I'm going to get 1 minus 2 times 1 minus 4. I don't want that. I just want this 2. So I'm going to divide by 1 minus 2 times 1 minus 4. All right, now how did I get this? How do I get just this 0 piece? Well, that's when x is equal to 2. So when x is equal to 2, the first and the third summand go away. And so I just get this last one, and I just want to divide then by, well, when x is equal to 2, I get 2 minus 1 and 2 minus 4. And then finally, for this third summand, that's when I let x equal to 4 so that the first two summands are 0. And so now I want x to be 4, so I divide by here 4 minus 1 and 4 minus 2. So this is going to be a quadratic. Why? Well, again, I have a constant, I divide by a constant, all three of these. And in the numerators, I have quadratics, right? If I distribute these, right, this would be x squared minus 6x plus 8. And this would be x squared minus 5x plus 4. And this would be x squared minus 3x plus 2. And if I want to go through all the algebra, I can consolidate this down to one single quadratic. All right, so that's the idea behind Lagrange polynomials. You can go to any dimension you want. You're going to expand in exactly the same way. You write down the output values of the, say, n points that you have. And then you're going to multiply in the numerator by, well, x minus all the other inputs, right? Not the one corresponding to that output. And then you just divide, right, by constants so that when you evaluate at the right point, these coefficients become 1. Okay, so that's how you can start getting into the idea of what is a Lagrange polynomial. This is a very vast, interesting subject, and I'm not doing justice to all the incredible theory out there. But in case you, for example, want to know why Simpson's rule works, and you say, well, how do I know that if I chop up my interval into 2 segments and I take, right, these 3 points and I sample my function at those 3 points, how do I know I can build a quadratic that goes through those 3 points? You can just use one of these Lagrange polynomials, and that'll do it. All right. Have a wonderful day, everybody.